Okay, I think we're going to go ahead and get started. Welcome to Nano at Tech on February 7th. And before I introduce today's speaker, just a quick word about our next meeting 2 weeks from today on February 21st. We'll be treated to an external speaker, someone from outside Georgia Tech, Dr. Grant Johnson from Pacific Northwest National Lab. And so check your email for the usual flyers about that. So it's a real pleasure to have with us today Professor Xing Xie from the School of Civil and Environmental Engineering here at Georgia Tech. Professor Xie got his bachelor's and master's degree, his first master's degree in environmental science and engineering at Tsinghua University, and then got a second master's in materials science and engineering and his PhD in civil and environmental engineering at Stanford University, and then did a postdoctoral stint at Caltech before coming to Georgia Tech in 2017, where he is currently the Carlton S. Wilder Jr. Professor in Civil and Environmental Engineering. He's won a number of awards, notably an NSF Career Award in 2019, awards from the American Academy of Environmental Engineers and Scientists, the Sustainable Nanotechnology Organization, and in 2021, the Civil and Environmental Engineering Young Faculty Research Award. And with that, I will turn it over to you.
Okay. Thanks, Dave, for the nice introduction. And then thank you all for joining today's seminar. It's my great pleasure to be here and share what we have done in the past few years using LEEFT technology with nano materials, mainly for water disinfection. So let's go ahead and then talk just a little bit background about water disinfection. So as a number you can see here, currently still more than 10% of the population in the world don't have access to safe drinking water. And millions of people die from waterborne diseases, and then a significant number of them are children under 5 years old. The reason for these diseases are really the pathogens in the contaminated water. So these pathogens can be viruses, bacteria, protozoa, and helminths. So this is actually a slice, pretty old slice. I made it during even my PhD time, like more than 10 years ago. But the numbers here, I just tried these numbers before, and it's pretty much similar. So there's slightly difference, but still pretty close to these kind of significant numbers here. So that really means that we still haven't done a good enough job in terms of doing water disinfection, which means that we use different methods to either remove microorganisms, these pathogens, from water, or inactivate those microorganisms in the water. So the most widely used water disinfection currently in our like water treatment facilities, they're pretty much more than 80%, 90% they're using chlorination. So we actually started to use chlorination about 100 years ago in the United States. So as you can see from this curve, which shows the life expectancy over the time, so you can see, after this we start using chlorination, the average life expectancy really grow very fast. There are definitely some other reasons causing, making this improvement, but really just treating the water, chlorination, killing the pathogens, microorganisms, really play a very important role there. So really because of this, actually, our National Academy of Engineering rate the safe and abundant water supply as the number 4 of the greatest engineering achievement in the 20th century. So this is a really great achievement in the last century. But at the same time, as I mentioned before, we're still not doing a great job, good enough job in terms of doing water disinfection. It's really because another thing we have, basically we treat the water, but we're generating another problem, which is a disinfection byproducts. So this is really a so-called chlorine dilemma. So basically, this is a disinfection process. Basically, we kind of reduce the microbial risk of drinking water. So basically, we remove mass pathogens, but basically there are some other organic matters in our drinking water which will react with chlorine, and then will produce some harmful disinfection, basically harmful products. We call it disinfection byproducts, and then some of these has been demonstrated to be carcinogenic. So we already have some regulations to regulate certain type of disinfection byproducts in our drinking water, but there are thousands or even millions of different kind of disinfection byproducts which we won't be able to regulate all of them. So there's a lot of uncertainty there, but overall, when we are trying to make sure our drinking water pathogen-free, we are producing another problem, which is disinfection byproducts. So in the past few decades, people have tried different methods, tried to develop alternative methods to do for the chlorination, for example, UV ozonation or different kind of technologies. But overall, there's still some limitations or drawbacks. That's why currently still more than 80%, 90%, it really depends on the countries, but still majority of the water treatment plants, they use chlorination as their main disinfection process. So that's the main motivation behind our research. We have been working on this so-called locally enhanced electric field treatment technology, trying to really develop eventually chemical-free or at least chlorine-free disinfection methods, which can be really largely implemented in the future for our next generation water disinfection process. So let's get into this technology. So let's look at to learn what's the locally enhanced electric field treatment. We need to know what's the electric field treatment first. So this is a schematic showing the electric field treatment process. Basically, this is a schematic showing we have a positive electrode, we have a negative electrode. In this case, if they are parallel electrodes, we will be able to generate a uniform electric field strength between these two electrodes. So these orange lines here indicating the direction and also the strength. And then these shapes indicating the microorganisms when they expose to the electric field. What happens is that the ions in the solution, the positive ions will move towards the negative electrode, and then the negative ions will move towards the positive electrode. So basically, the movement of these charged ions will generate a so-called transmembrane potential or transmembrane voltage across the cell membrane. And then this strength, the transmembrane voltage, will really proportional to the strength of external electric field. So basically, when the external electric field reaches a certain threshold, you actually will be able to generate a pulse because of the transmembrane voltage or potential. It also really depends on the strength, and then basically that determines the size of these pores and then how long these pores will last. So if the strength is kind of moderate level, these pores can actually be able to recover or reseal, and then we call it reversible electroporation. And then this process has been widely used in biomedical field for drug delivery, gene delivery, these kind of applications. But if the external electric field strength is high enough, and then basically this pore becomes irreversible, and then these microorganisms will be able to be inactivated. So in the basic idea we have here, we basically try to create a situation for this electric field treatment process is that we want to reach a strong enough electric field treatment, and then in that case we generate irreversible pores, and then basically use these for microbial inactivation processes. So and then the biggest challenge here basically is that we know that the electric field strength is defined as the voltage divided by the distance. And then for the certain treatment process, you won't be able to use, especially for large scale treatment, you won't be able to use a chamber that's very, very narrow. So at least it needs to be millimeter scale or even centimeter scale. So that's why in this case, we really need to apply a very high voltage, even more than several kilovolts, to realize a strong electric field that's high enough to kill microorganisms. So that's the biggest challenge for large scale water treatment. First of all, it's very energy intensive, and also it's not safe for large scale application. So that's why basically, as I mentioned, there's a motivation behind our development of the LEEFT technology. So basically, we try to we basically come up with this idea. We try to use a locally enhanced electric field. Basically, it's ununiform electric field rather than a uniform electric field between the two parallel electrodes. We try to locally enhance the electric field. So in that case, we don't need to apply a very high voltage. It's just a much smaller voltage. But within the chamber or within the system, a certain area, we have a locally enhanced electric field that's strong enough to kill the microorganisms. So there are two general strategies or directions or two different scales we can realize this locally enhanced electric field treatment. So one is that we call it macroscale enhancement. The other is a microscale enhancement. For macroscale enhancement, basically we can try to design the system, design the configuration of the electrodes. So for example, we can have a center electrode, positive electrode at the center, and then we have a negative electrode as a coaxial outside electrode. So in this case, basically based on the physics, we know that at the center, basically if you do the electric field strength calculation, we know that at the center, the electric field strength will be much stronger than the outer ring. And then it really depends on the size and also the ratio of the inner and outer diameter. And then the strength can be easily enhanced to be at least tens of times compared to the normal background electrode if you apply two parallel electrodes. The other strategy or the other scale is a microscale. It's basically, we notice that if we modify the surface of a parallel electrodes with tip structures, we can achieve a much stronger electric field strength at the tips of these tip structures. And also it really depends on the size of these tip structures, especially the aspect ratio of these tips. The enhancement can be even several orders of magnitude. So let's basically, again, the main goal is really want to use much smaller voltage to realize within the system at certain location, we have strong electric field that can kill microorganisms. So to realize this strategy, we have combined these two kind of scale of enhancements to develop our kind of prototype to realize this treatment. So this is the tubular coaxial electrode configuration. So basically we have a center electrode and then we have an outer electrode and then we modify the center electrode with these tip structures. Okay, so we also did some simulation to make sure this is really follow the design, and then we can we use this color to indicate the electric field strength. You can really see near the tip structures of at the center electrode, you have much stronger electric field. This is the image of the first prototype developed in our lab. So it's just a very small system, only about 10 centimeter long and 1 diameter tubular shape of the treatment chamber. So just show you a little more detail about how we made this system. So basically, as you will probably notice that the center electrode is really the core electrode of the system. So we fabricated the material, the electrode we use for this demonstration is the polydopamine or PDA-coated copper oxide nanowire modified copper electrode. Okay, so basically we start with a commercially available copper wire. This is actually pretty cheap material, commercially available. We just purchased it from McMaster, a widely accessible supplier. I think for one roll of this copper wire for 1 mile long is only about $10, so it's pretty cheap material to start with. And then we just heat it up at the atmosphere with oxygen and a certain temperature. We will be able to grow copper oxide nanowires on top of this copper wire. And then we do another step of polydopamine coating, really just want to make sure the electrode is kind of protected a little bit or stronger or can last longer. And then the polydopamine is really a very easy process to coat it on the surface. Basically, you prepare a dopamine solution and then put the electrode in the solution, and then you control the temperature, control the kind of oxygen level. You will be able to control the growth of polydopamine layer on top of the electrode. So just show you a little bit more SEM images. Because we did all this characterization in the facility here at IEN. So you can see the core, the center electrode is about 80 micrometers, so it's actually very thin. So industry has already done a pretty good job in terms of producing, these very thin copper wires already. So the center electrode is less than 100 micrometer in diameter, and then after the growth of the copper oxide nanowire, this is the image showing the a very dense copper oxide nanowire on the surface. And then you use TEM, we can see also the dopamine coating layer. We also do the basic elementary analysis to demonstrate, to really quantify the thickness of the polydopamine coating. Basically we can control the polydopamine coating precisely. So just show a little bit of a performance. We use this device to basically demonstrate that with a reasonable flow rate, with a reasonable voltage, also very low voltage, only 1 volt, 2 volt, we can achieve pretty high inactivation, more than 6 log, which means that 99.9999% of the bacteria in the system have been inactivated. So in this test, we pretty much still use E. coli, which is a model bacteria, and then we prepare synthetic water in the lab in a very well-controlled environment. And then next step, basically we try also different bacteria, gram-positive, gram-negative, and then we also try natural water, river water, and then we dose the natural water with some E. coli to do the similar experiments. But again, basically we show high performance, high inactivation efficiency with a reasonable flow rate. The dashed line here really indicates the detection limit of our methods, so the real inactivation performance can be even higher. So to be honest, this flow rate is still pretty low at this point. So it's just like 1 millimeter per minute. So you can imagine that the flow is actually not very high. So we have tried a little bit to scale this system up. So we produce this kind of about 2 meter long device. So we try to maintain a similar retention time, which means the time we use to treat the water. And then we basically realized a much higher flow rate. But to be honest, it's still kind of low comparing to the normal flow rate you can get from your tap. But we just want to demonstrate at least this is a scalable process, right? You can just have an even longer treatment chamber to realize that. And there's also a lot of other parameters we can optimize in our future work. Okay, so one potential application about these specific tubular shape coaxial electrode devices we have been thinking about is that we can potentially use that in our water distribution systems or in the pipelines. Currently, as I mentioned, we do the water treatment primarily in the treatment plant. And we usually, as I mentioned, use chlorination to do that. One of the very important reasons to use chlorine is that we can have some residual chlorine in the water, and so they can still provide kind of a continuous disinfection effect along the water distribution system. So usually we call this the disinfection process in the distribution systems. We call it secondary disinfection. So in the treatment plant, we call it primary treatment. So some of the current technologies, UV ozonation, they can easily replace chlorination in the treatment plant, but it's very difficult to maintain the disinfection effect along the distribution systems. So that's why one of the reasons that these cannot be easily, even they do in some plants, they do UV or ozonation, they still need to add some of the chlorination into the water before the water treatment plant send it out to the water distribution system. So basically the idea is that potentially we try to scale this system from point of use devices and a little bit larger to point of entry, or even a little bit larger to the water distribution systems, and hopefully eventually they can used in the primary water treatment, which is really require very, very large treatment capacity. But at least we feel like, in the water distribution systems can be potentially one scenario for the application. We don't need to replace all the pipelines, right? It's not necessary, but we can potentially replace some of the, pumping stations or manholes in those places, or the pipelines entering the buildings. Basically, some part of the pipelines can be potentially replaced with our LEEFT devices to provide additional disinfection capacity. We also noticed that for these kind of applications, the easiest way to get the power for the device, as you can see, we still need to consume some electricity, which is actually already very, very low compared to, for example, UV. But we still need to consume a little bit of electricity to provide like electric field treatment. But the easiest way to get this electricity is just directly from the flowing water. So we have demonstrated just using a small this kind of water generator that can provide more enough electricity used for these treatment systems. Okay, so and then basically this is a kind of first demonstration or proof of concept of the ideas we have, and I'll just show you a little bit more about the different aspects we have been working on along this technology in the next couple of slides, and then the last part of today's presentation, I'll just highlight some of our recent progress, especially with the facilities we have been using in here. So basically we have worked on really different aspects of this technology. One of the very important directions is the development of the LEEFT electrodes. As you can see, the center electrode with the nanowire modification is really the core of the technology. At this stage, we really need to combine the two scales of the enhancement to realize the microbial inactivation if we just use the LEEFT technology alone. Okay, so if you want to achieve a very strong electric field, we need to combine these two strategies. Especially, you need to use the nanowire modified electrodes. If you just rely on the design of the pattern of the electrodes, that's not good enough. But the nanowire electrodes, nanowire modified electrodes, really one of the biggest challenges is not robust enough. It's very fragile. It's not good enough for long-time application. So for the early generation electrodes, they only last for about 10 minutes, 20 minutes. And then we have tried different methods to replace the material from copper oxide to copper phosphide. We also do the PDA coating. So currently, the best electrodes we demonstrate in our publication is about a few days, but still under the highly controlled synthetic water, well controlled environment doing in the lab. So this is really not good enough for, it's probably fine for some emergency uses for point of use, potable water, portable devices for emergency uses, but it's definitely not good enough for large scale application. So so that's why at least there's still a lot of things we want to do. We want to push the lifetime of the electrode at least to be several months or even longer, that we feel like it's more comfortable to be used for large scale application. So that's why for now, for more practical applications, we actually have been thinking about whether we can combine the LEEFT technology with some existing methods. We are kind of sacrificing the enhancement of the electric field strength a little bit. We just use probably just one type of enhancement, especially using the electrode design in terms of a coaxial electrode design, just enhance the electric field trim a little bit. But we combine the system with existing methods. For example, in this case, we combine LEEFT with ozone. And then basically the idea is that we use LEEFT to increase the permeability of the cell membrane. So in that case, we only need to use smaller amount of ozone and to achieve the similar performance. So in terms of this synergetic effect, just a little bit more details. Basically, the idea is that LEEFT treatment is basically increase the cell membrane permeability, right? So even though it's still not the LEEFT treatment cannot inactivate the microorganisms directly, but it increases the cell membrane permeability, and the ozone will be able to diffuse into the cells easier, and then you will increase the ozone. Basically, the ozonation will be more efficient. Another effect is basically once you generate this kind of reversible damage on the cell membrane, and you have ozone nearby, so they won't be able to recover. So that also means that ozone will also improve the efficiency of the LEEFT itself. Basically, these two processes can be synergistic and produce better performance. Another example is that we combine LEEFT with copper. So copper also has well-known antimicrobial property, but usually we don't use copper for drinking water disinfection. It's really because usually you need to use basically more than a milligram per liter of copper in the water to have enough antimicrobial effect. So some places they use that in the swimming pools for water disinfection, or also in the hot water lines for water disinfection, but usually not use that for drinking water. You see, really because we cannot have too high of copper in our drinking water. So there's a regulation from EPA, which is 1.3 ppm, milligram per liter. So that's why we usually don't do that. But basically, we combine LEEFT with copper, and we demonstrate that. So in this case, for example, at this point, we only use 200 ppb, which is 200 microgram per liter of copper, and we combine that with this coaxial electrode designed LEEFT device. We achieve pretty high removal efficiency. So in this device, specific device, we only use the center electrode with the commercially available copper wire. So there's no any nano structural modification at the center. And then we basically, in this case, the electrode itself already basically is commercially available, even though you will consume the copper from the center electrode, but it's already easily scalable. It can be much ready for large scale or practical application. So a little bit more into the mechanism of this LEEFT copper system. So basically, in this case, the center electrode, we let the center electrode release copper in situ. So basically, we apply a DC voltage, and then basically the copper is released from the center electrode, and then basically you can see these gold dots, yellow dots indicating the copper ion. So you can see because it's released from the center, so the copper concentration at the center will be stronger. And also, if you remember that the center electrode will also have stronger electric field near the center. In the meantime, is that most of the microorganisms they are negatively charged. So that means that during this water flow, we believe most of the microorganisms will be attracted to the center electrode as well. So basically, near the center electrode, you will have stronger electric field strength, and then higher copper concentration, and also higher bacterial concentration. So that really makes the whole system work synergistically to achieve a very high performance. Okay, so here just show, basically show a short video. We use a special device called TNG, which is a triboelectric nano generator to power the LEEFT copper system. Let me see, I can play the. Yeah, so basically this is a hand pump, and then once you rotate it, and then that provide a driving force for the flowing water. And at the same time, this hand pump, this rotation also generate electric pulses, and that can be used to drive the release of the copper ions, and then do this disinfection. So this is just one type of application we have developed. We also developed another type of power source, basically use our cell phone to drive this LEEFT copper device. So this is just a simple device that can directly plug into your cell phone, and then we develop this kind of interface. You can either control the voltage or control the current of the system output. So that's basically a kind of a general overview of this technology and also the different aspects we have been working on. So for the rest of today's presentation, I really want to focus on some kind of recent progress we have done with the help of the facility IEN. So basically, we have shown that we have developed different devices. And then we know that these devices work pretty well to achieve very high performance. And we also know that the nanowires in this system really play a very important role in terms of achieving a very high performance. But the problem is that we're still not really 100% sure how these microorganisms being inactivated and what's the interaction when the bacteria flows through the electrode, what's the interaction between the microorganisms and the electrode material. So this is really like a black box. We know water flow in, flow out, and microorganisms get inactivated, but we really don't understand clearly what happened inside. So we have been asked from the reviewers during our manuscript submission process. We only measure the beginning and in the end, but you don't know whether you have also oxygen species generation, or you also have temperature increase, or any other chemical reactions inside the blab in this reactor. You probably won't be able to measure in the end, but basically what we try to do is using this. We try to open this black box. We try to use this basically operantal characterization methods to study this process, and then that's why basically we develop these kind of lab-on-the-chip devices, and then do this in situ LEEFT treatment, and then really look at the mechanism, look at the detail. So a little bit more detail about what we have done here. So basically, these are the chip devices we developed. So this is just a normal glass slide, and we have two pad, large gold pad, which we use for the electricity connection. But between the two, we have this gap, and then we have these nano wedge structures or nano tip structures. So we have been optimizing this design for a while, but basically we try to create very sharp tips, but at the same time we want them to be very stable and also want them to be visible under the microscope. So that's why we end up with this structure. We have you can see the length is about 8 micron, and then the top is 200 nano, and the bottom is 1 micron to make sure it's standing there very stable, even though after multiple washing steps. The size of these nano wedges are still not ideal, or basically when we produce the devices, when we grow nanowires, it can be even smaller. But this is pretty much the most stable or smallest feature or highest aspirational features we can produce repeatedly between these gaps. But it's good enough for us to really demonstrate this process, to study the LEEFT process under the microscope. So, and basically what we do next is we treat the surface with polylysins, basically to immobilize our model bacteria. In this case, it's Staphylococcus, because it's a round-shaped microorganism, one round-shaped bacteria, which is easier for us to look at. And then this is how it looks like once we have these microorganisms being mobilized on the surface. And then we basically put it under a microscope. We do a LEEFT treatment. And then we do, we do different staining methods to look at what's really happening on the surface. Okay, so again, so here is the chip before any LEEFT treatment. We also did a console simulation to make sure with this configuration, the electric field strengths based on the simulation, based on the theory, the electric field strengths near the tips can reach the kind of a threshold of the electric field strengths that can produce irreversible electroporation. Here is with the microorganisms being loaded, and then here is basically typical results we achieved in our experiments. So again, this is another short video. When the time hits 0, that's the time we start the electric field treatment, and then you can see basically these places, basically the line here indicating the location of the tip structures, and then we can see that probably one more time. Basically, you can see near the tip structures, you will see the cells being light up with by the dye, and that really indicates the inactivation of the microorganisms. So you will see some kind of dots, or even they are already dead cells that show the red color. But most of the cells, if they are alive, they won't have the red color, because the color indicates basically how much the membrane has been able to prevent the diffusion of the dye into the cell. So if the cell has been inactivated, the dye will be able to diffuse into the cell, and indicating that we basically consider the cell has been inactivated. They are not maintaining the integrity of the structure. Okay, so and then after we do some image processing, basically we remove the background, the dead cells originally before experiments. This is the final results we got. So basically, we can see that only those locations near the tip structures, you have achieved a very strong electric field strength. You have the cells being inactivated. Okay, so this is basically the platform we developed, and then basically we use this platform to do a more comprehensive study with the LEEFT structure of the LEEFT treatment. So one of the very recent kind of progress or achievement we demonstrate here is that originally the electric field treatment usually will apply microseconds of pauses. Basically, that's also what people have done in the conventional electric field treatment. But basically, in our experiment, we try to see is that whether we can use even shorter pauses to basically see how fast this electric field treatment can be. So I just want to directly show you that this is a result that we recently achieved, is that we only need to use a single pause of 20 nanoseconds with a certain level of the electric field strength. And then this is just one treatment, okay, very fast, 20 nanoseconds at time 0. And then we monitor the strength of the basically the reflorescence intensity in the individual cells. So you can see after this treatment, and then the fluorescence will increase along the time, and really indicates that the irreversible electroporation has already happened after this treatment. So show you some images. For example, this one, right? So before that there's no any reflorescence. After treatment, you will see you will start to see the diffusion of the dye into the cell. And I also want to point out that the diffusion point is clear to be somewhere very close to the tip. So it's not from a random direction. In most cases, it's just from the point that's very close to the tip structures. Here's just another image showing a much faster diffusion. So basically here you can see the time is still a couple seconds, but really this is not the limit of the treatment itself. It's really limited by the diffusion of the cell, diffusion of the dye into the cell. Okay, but the treatment really happened very fast. It's only like 20 nanoseconds. So we also compare this treatment process with a conventional electric field treatment. So basically that's those structures we don't have any nano wedges as you show in the previous slides. And then we can summarize the result like this. Basically, again, so we fix the pathways as 20 nanoseconds. As you can see, for the longer effective treatment time, basically means the multiple passes, right? So if it's 200 nanoseconds, basically means that we apply 10 of these electric passes, right? If it's 20 milliseconds, it means that we have applied 1 million of the electric passes to try to inactivate the microorganisms. But as you can see from the summary of these results, even with much longer treatment time, right? Even 1 million, 10 million of these short pauses, the conventional electric field treatment won't be able to achieve very high inactivation efficiency. The maximum is still like about 20%. But if we use the LEEFT treatment process, okay, so you can see the performance generally is much better. Right? If you compare the similar electric field strengths, the 55 kilovolt per centimeter, so that's the 55 kilovolt per centimeter, we actually only use one pass of 20 nanosecond to achieve a much higher, like about 60% inactivation, which is already better than the 1 million or 10 million of the passes used a conventional electric field treatment. In other case, if you allow a much longer treatment time or multiple number of passes, basically that means that LEEFT can use a much smaller electric field treatment strength or much lower voltage. Okay, so basically the summary is that with LEEFT, the electric field strength can be reduced by 8 times. So this doesn't seem to be a very significant number, but actually it really indicates a much smaller energy consumption. But more significantly, the treatment time can be much, much faster. So it can be 1 million times faster than the conventional electric field treatment in this specific case. Okay, so yeah, and then basically we further spend some more effort trying to see whether we can do a better job in terms of basically showing what's really the mechanism behind for this ultra-fast electric field treatment process. So we have designed pretty much these following 3 slides or 3 different experiments to demonstrate that for this ultra-fast microbial inactivation process is really the electroporation playing a major role, playing a dominant role in terms of microbial inactivation. So first is this one. Okay, so basically one specific or unique property of the electroporation is that with a little bit minor condition, either the shorter treatment time or a little bit smaller voltage, you will be able to realize reversible electroporation. This is really a very unique property. Comparing to chemical treatment or thermal treatment, you won't be able to stop the treatment at the middle of the time. So it's basically if they will be treated or they are not treated. Like basically the cells will either not die or die, right? So, but in this case, as you can see from the results, what we'll be able to demonstrate is that, okay, so all these lines indicating one individual cell, what we'll be able to do is that, so basically the pink area, we basically turn on the treatment, and then the gray area we turn off the treatment. So what we can do is that when there's no any LEEFT treatment, again, the fluorescence intensity doesn't change. And then we turn on the electric field treatment, you will see the intensity start to increase. And then, but if you turn it off, they will be able to stop right there. And then basically that means that the pore or it will be basically closed pretty much instantly. So, and then you turn it on again, and then you will see the increase, and then turn it off, and then the diffusion of the dye will stop right away. So this is a very, as I mentioned, very unique property of reversible electroporation. So any other treatment, like thermal treatment, if there's a damage, the damage won't be able to recover instantly after you remove the treatment. Like, for example, you remove the heat source or something like that. And then, after this on and off for a certain time, eventually the cell membrane will completely disrupted, and then there will be the significant increase of the fluorescence, which indicates that irreversible damage has been generated. So, yeah, so this is basically, as you can see, we use a much kind of a smaller voltage, smaller intensity, demonstrating that under this condition, you definitely have this reversible electroporation. And then basically that also indicates that with some kind of stronger electric field treatment, you will be able to realize the irreversible electroporation in the system. The second experiment is that in this case, we will be able to measure the ROS, which is the reactive oxidative species generation using the staining methods in the system. Before that, if we just have the device, we may generate some ROS near the tip structures, but we won't be able to measure it, but they can be easily, diluted when you are measuring the ROS generation in a bulk water. In this case, we use a staining method to show that with much longer pulse width and also a certain high electric field treatment, you will see this green color indicating there's some oxidative species being generated, which really play a very important role in microbial inactivation as well. But if we use a 20 nanosecond pulses, you can see there's no ending for green fluorescence. At least that's indicating the detection limit is below, the concentration is below our detection limit. We're still not 100% sure there's no ending, but at least it will be much less ROS generation comparing to the longer pulses. But under these conditions, we can still demonstrate that more than 90% of the bacterial inactivation near the tip structures. And then we believe most of these in this case, most of the microorganisms being inactivated really due to the electroporation rather than the oxidative species generated with the longer pulse widths. The last one is really also a very strong support. Evidence is that we run the experiment with some, we call it floating nano wedges or suspending nano wedges. Basically means that these nanostructures, nanotip structures, they don't have to have the direct contact with the bulky electrode. Just as you mentioned, just as you see, we have two large gold pads on each side, and then these nano wedges they're just sitting in between, but without direct connection. But also demonstrate that they can achieve similar microbial inactivation near these tip structures. We also be able to pattern this kind of GT side, and then also light up these microorganisms to show this very nice GT side in our. We put it in our paper, so show the GT image there. Yeah, but this is also a kind of a control experiment. In this area, we have these nano wedge structures, and then the other side is just basically the gap between the two electrodes, and then we can see a significant difference. So basically, this is a really indication that the treatment, the inactivation process is really due to the electric field treatment rather than electrochemical reaction. If it's a electrochemical reaction, right, that only happens on the two electrodes that's directly connected to the circuit. You won't be able to have electrodes inserted in between and then achieve the same electrochemical reactions. Okay, so with that, I really want to just summarize the presentation with these slides showing basically the kind of demonstrated or also potential advantages of our LEEFT process. So we really believe this technology can be a transformative water disinfection methods in the future. Some of these advantages we list here has been demonstrated in our experiments. Some of them are still waiting for us to prove that. But basically, this process can be really high efficiency, very broad spectrum for different pathogens. Specifically, we recently demonstrated it can be really, really fast, ultra fast treatment process. Hopefully, this can be also low capital cost, really relies on how challenging we can produce the nanowire modified electrodes. One of the intrinsic advantage of this process is that it's supposed to be an electrophysical process, because we really rely on just the movement of ions like a physical scissor, like ionic scissor, to cut off the cell membrane to inactivate the cells. So theoretically, this is a physical method without generating any chemical disinfection byproducts. And then some other advantages, including there's no over-treatment concern, right? So it doesn't like chemicals. You need to control precise doses. You don't want to add too much chlorine in your water. That will cause problems as well. But in this case, in our case, it doesn't matter. You treat the water too long, and that's no any problem. It's also easy to operate, pretty safe to operators, and then no any other secondary pollutants as well. Okay, so with that, I really want to just thank all my students, specifically 2 students, Team 1, who is sitting right there, and then she did most of the operational studies with making the chips, doing these observations. Also, my previous PhD student, Jianfen Zhou, and then he is currently a faculty at GTSI, Georgia Tech Shenzhen Institute. He did most of the early stage development in terms of developing these coaxial electro LEEFT systems. Also want to thank all my funding supports, NSF, and also the INC grant, which also helps us a lot in our early stage development. Okay, with that, I would like to thank you all for listening. I'm happy to answer any questions you have.
All right. Questions?
Never shy. I'm curious, when you were showing the combination of the LEEFT with the ozone, what sort of flow rate reduction could you achieve? Because ozone alone is going to have some limitation in its flow rate. Did you measure what flow rate reduction you could get or flow rate increase you could achieve by combining them?
So for the LEEFT ozone system, we don't have a continuous flow system. So we have the LEEFT treatment is just a flowing through treatment, but for the ozonation we actually use a batch system. So we just I think we fixed the treatment time. I don't remember exactly, it's about 1 minute or 2 minutes, very short treatment time. But we really adjust. I didn't show any results here, but we just adjust the dosage of ozone. But generally speaking, basically we can reduce the ozone dosage. It really depends on how much LEEFT we use to treat the microorganisms, but we can reduce the ozone dosage to about 1/3 to a half. for the similar performance. Yeah.
Thank you. Very interesting talk, presentation. I have a question regarding your tubulars structure, how to scale. If you put it on one almost 2 meter long, is linear. I didn't get it for the scale. How do you tubulars get a scale to that 2 meter long? If you flow in the one direction, that's you know my question.
Well, so in this case, right? So we still have the outer electrode. The outer electrode in this case is basically the copper wire or stainless steel, copper tube or stainless tube. You can directly use it as outer electrode. So it's actually very challenging for us to hand the center electrode, going through this coaxial design. But if you want to, we haven't gotten to the stage to really design some commercially available large-scale products. But you can imagine that if you want to take a turn, right, it's very difficult to hand the electrode when you take it when there's an angle, right, when the pipe turns. But you probably want to install this at these locations when you have linear sections in the pipeline systems. But I mean, you don't have to have the electrode being connected all the time, right? So you can have different sections. They can be connected in series or in parallel for the treatment.
So how to prevent the shorting? You said it here.
Yeah, so that's a good idea. That's a good question, right? So you need to make sure, within the pipeline systems, you need to make sure the center electrode doesn't touch the outer electrode. But of course, there's a lot of challenges or questions we need to solve if we want to really design the commercially viable product. Yeah, go ahead.
I wanted to ask about the results you showed where you were turning on and turning off the reversible porosity or electroporation. So it looked like the ones that didn't fail, or at least didn't fail initially, were on the negative electrode, and it was the positive electrode where you saw the irreversible happen very quickly. And I was just curious, is that a result of the field being lower at the negative electrode, or is there something else going on?
We actually did not observe significant difference between the positive and negative electrode. Actually, I forgot to mention that. That's also a good indication that this is the electric field treatment rather than electrochemical treatment. Because if electrochemical treatment, the positive and negative electrode will have different species being generated by different reactions. But in our cases, actually, we just pick some of them to indicate in the process. But we really want to show that both the negative electrode and positive electrode, we both observe this similar phenomenon actually. If it's, I think in our treatment process, it really depends on the duration of the process, right? If it's short enough, it will be the electric field treatment being the dominant inactivation mechanism. When the processes are longer, for example, when the process is 2 microseconds, we do see some oxidative species generated at pretty much on the positive electrode, and then that will contribute to the microbial inactivation for sure. Does that answer your question?
I guess, but on the slide just before, it looks like the two that show the quick turn.
Oh, these two?
Yeah, those are both positive.
Oh.
I mean, it could just be luck of the draw.
Yeah, T, maybe you can.
So I did this experiment. So it's just the fluorescence is kind of random how high they jump. So it's like I took a video and there are like 20 cells. So I just randomly pick 4 cells, 2 on the positive and 2 on the negative. And they showed similar phenomena, which means that they jump and they stay and they jump and they stay. But how far or how high they jump is quite random because it's just a very small cell and a very quick dye inflow. Yeah, so if I pick more cells, they may show a different level of jump, but they show the same phenomenon, which means that they jump and stay and jump and stay. Yes, and so the final big jump. It's just they are finally inactivated. So the pore cannot close anymore. So they just allow a big inflow of the dye. Thanks.
I see. I think a specific inactivation, for individual cells were also affected by how close they are, to the tips. So they will affect how much damage they receive for each short treatment period.
Any other questions? I have one. Why polydopamine?
So it's really because it's very easy to generate a coating. As I mentioned, you just need to prepare the monomer solution. You put any kind of feature, especially we have these kind of nano tape structures, so the surface you can consider is very, very rough. And then polydopamine coating is one of the easiest methods that you can produce nanometer. We can control the thickness of the polydopamine layer in the nanometer resolution. So that's the original idea. We try to use polydopamine. But I think we also try different coating now to see whether they can produce an even better protection, also not affecting the electric field distribution.
Okay. If no more questions, let's thank our speaker one more time, and we'll see you in 2 weeks.
Okay, thank you very much.